I'm going to discuss MUP1 ligands and pheromones to give you a better idea about the research that goes on in this stream and also to prepare you for Experiment 9 and the Undergraduate Research Forum. So first of all, to think about MUP1 ligands and pheromones, we have to remember the definition of a pheromone versus a ligand. Now, a pheromone binds to a protein and causes a physiological response, a physiological change in the mouse. A ligand is simply something that binds. Therefore, all pheromones are ligands, but not all ligands are pheromones. So here are a few pheromones that are shown. This is hypothesized to be a pheromone, but the function is unknown. So this is excreted from male mouse urine, and it causes puberty acceleration in females. So the male comes around, the females begin their puberty early, and they can mate, that type of thing. Here we're showing some other examples of pheromones, and this 2,sec-butyl 4,5-dihydrothiazole, or SBT, you may remember from your PIMOL modeling exercises. But I want you to just look and see these structures and the variety of scaffolds that MUP can bind. And by scaffold, I just mean these kinds of heterocycles. So this one with the 2 nitrogens, this ketone. So there's quite a few different molecules that MUP can bind. And so here, SBT causes estrous synchronization, which means all the females go into heat at the same time, and also accelerates their puberty. So you can see your pheromones have a lot to do with mating. So now I just want to introduce ITC, isothermal titration calorimetry. This is the experiment that we do once we synthesize our ligands for the MUP1 protein. Here, we have a stirring syringe that contains your ligand solution. And this is dripped into a protein solution in the sample cell in set increments. Each time that a set increment goes in, heat is given off, and you can see these spikes on the right-hand side. And after a while, this starts to kind of level off and flatten out here. This is because the protein is becoming saturated, and to have a successful ITC experiment, the protein must undergo saturation. From the data you obtain, the slope here is related to the Ka. The stoichiometry can be determined, and we expect this to be 1-to-1. MUP has a small binding pocket. We expect one ligand to go into that binding pocket, but there's often some experimental error that causes N to deviate slightly from 1, as you'll see in some of the data. The enthalpy is for high affinity binders related to the y-intercept. And if you look at these equations, for delta G, you can see delta G is free energy, and when delta G is negative, processes are more spontaneous, so binding is more likely to happen when delta G is large and negative. This is related through these equations, and we know the temperature we run ITC at. We know R is the gas constant, and with the log of the Ka that we get from this graph, we can solve for delta G. And since delta G equals delta H minus T delta S, we already have delta H from this graph as well, and we can get this entropy term, which has been historically harder to quantify. So Ka is binding affinity, and that's how well something binds to the protein. But the whole story of why things bind well are related to this enthalpy and these enthalpy and entropy terms. So here are some studies of different ligands for MUP1. And this study was done by Homans, our collaborator for this project. And here he was adding carbon atoms and lengthening a chain on these alcohols. And they found as the chain size increased, the binding affinity also increased. And this was due to enthalpy. Okay, and so the extra carbons are making more van der Waals contacts within the active site, and enthalpy goes up, driving up Ka and delta G. Okay, so extending chain length is good. We have a low binding affinity here, and we can see this introduction of a second OH group in this particular study was unfavorable. SBT has also been examined, and you saw this in your background. This small chain right here only binds on the order of 10 to the third. However, SBT binds on the order of 10 to the sixth with a highly enthalpy driven binding, and this one doesn't increase too much as we get up here. But overall, Ka and delta G do go up. So here they were looking at binding, and notice this chain is very small, but this Ka value is large. This is actually bound to MUP4, and MUP4 is different than MUP1. It's an isoform. It has like 70% sequence similarity, but the active site is a little smaller and shows higher binding affinity for SBT and subsequently this methyl thiazoline. Well, they introduced other things that could hydrogen bond, and this one with the nitrogen that can hydrogen bond in the active site is pretty good as well. This nitrogen can also hydrogen bond, but the oxygen, it just steals the electrons away through this dipole that could be there, and binding affinity, as you can see, goes down by 2 orders of magnitude. Now, when hydrogen bonding is not possible, we don't see binding at all. And here is a picture showing how this works. So SBT binds to 2 water molecules in the active site, and you might remember this from your PyMol, which binds to, here it's labeled tyrosine 138, but it really is tyrosine 120 in most of the literature, so they just had a bit of a different numbering system, which is fine. We can just subtract 18 and figure out where all of our residues are. So this is a contact diagram generated in something like ChemDraw that's showing you this hydrogen bonding network. So here were some questions we would have discussed if I were here, and I apologize for my absence. But these are good things to think about. The objective of a study, what was their hypothesis in doing this? Well, they wanted to look at the carbon chain extension, and what did they find? Well, they found better binding and generally based on enthalpy. So here we're looking at another ligand that binds to MUP1, and this ligand, HMH, hydroxymethylheptanone, was also in the paper that you used to create your PyMol structure. And so this one also binds to the water-mediated network, and it shows weaker binding than SBT. So in our stream, we looked at compounds that were analogs of this known ligand. Now, this wasn't the pheromone that I showed earlier. This is a ligand that was explored by Homans and has particularly high binding affinity for MUP1. Well, we said, this guy binds to MUP1 through a hydrogen bond right here with tyrosine 120. So maybe if we make ligands that are more basic, that bond will be even stronger, and maybe we'll see stronger binding due to increases in enthalpy. And we've had a variety of students working on this over the years. These syntheses have changed, and so this has been an ongoing project. But recently, we were able to synthesize the 2 ligands that we were targeting in our stream, and this is the data from this paper by Homans. So you can see with this extra carbon on the chain, binding affinity is a little bit better due to enthalpy, and entropy kind of stays the same here, okay? And in our ligands, well, this one is pretty darn similar in profile to this ligand. However, our pyrimidine that Christopher Ching recently synthesized showed an incredibly large enthalpy of binding and really unfavorable entropy, which we haven't really seen with any binders of MUP1 to date. So we got a crystal structure of this compound, and we saw that in general, it's this nitrogen right here usually forms the hydrogen bond to tyrosine 120, but it's not in range. Actually, our methoxy group is making the connection, and there's an extra water in here. So compare this with this structure. We can't see any water molecules in the active site in this one, and the hydrogen bond is direct to tyrosine 120 from the, this is a pyridazine itself, and this is a pyrimidine. Just the naming has to do with where the nitrogens are in the ring, and so hopefully you'll get to learn some of these names over time. But we have 2 hydrogen bonds, and it's dramatically different binding. And so go see Christopher's poster at the Undergrad Research Forum, and he can tell you all about that. So we're also looking at changing R groups on phenols, and we've looked, propylphenol is just 3 carbons, isopropylphenol, and pentylphenol is 5, so this is increasing chain length, and we do see increases in R binding affinity as well, and R binding is also driven by enthalpy. These are other compounds that Priscilla and Aisha are looking at. However, we don't have enough data yet to say this is definitive. We don't have 3 data points for each of these, but this is a work in progress. And our phenols bind a little funny. Look, it looks like they're almost twisted through each other. Well, this actually isn't possible. What is happening in the active site, this is the isopropyl ligand here. You can see the little chain. That's 3 carbons that branch out. So that's an isopropyl right here. It's shown in a ChemDraw structure. And it either binds like this or binds like this. And 50% of the time it's like this in our crystal structure, and 50% of the time it's like this. So interesting, but a little harder to correlate. And I just wanted to show Priscilla's synthesis in this as well. She synthesized this particular compound, which we're still working on. So these are the types of projects that go on in the stream. Now, we're also interested in this topless study. This is the original scheme from the topless paper where he described how to substitute aromatic compounds. So start with a aromatic compound, a phenyl ring, the benzene ring. It has an H on it. Well, then try making it with a chloro at the 4 position. Okay, so across from another group. That's the para position. You can look at this up if you're interested. So we put on this chloro, and then if binding is lower, we follow this side of the tree. If it's equal, we follow this side of the tree to optimize binding. And if the chloro compound binds better, we start making these compounds with a 3,4 dichloro on there. So let's look at this spelled out a little bit with an older study that we did. So we were looking at thiazolines with phenyl rings. And this one had just a phenyl ring on it with an H. Sarah Jin, an old mentor of ours, and Ernella have worked on this as well. Karen Ima synthesized this compound with the chloro, and a few students started filling in the tree, and we were interested in looking at this activity. Well, this study fell short because we were actually having solubility problems at the time. However, this is something that has recently been maybe solved in the stream. We found a different buffer for isothermal titration calorimetry in which these compounds may be more soluble. And so we do plan to pick up this study, and Adriana is very excited to pick this up in the summer. So we'll be looking into this stuff again, but you guys are looking at a little bit different of a topless study because we just have compounds kind of waiting to be solubilized for ITC here. So here's a topless tree for side chain substitution. And I guess I kind of missed saying this on the last slide, but the study looks at the electronics of the groups that are on the aromatic ring, and also how greasy the compound is, how soluble it is in water versus how soluble it is in hydrophobic environments. And this is important in the body because you need a level of water solubility because we're aqueous, but you also need some level of lipophilicity so that the compounds can make it through cell membranes and actually get to their protein targets. Okay, so that's, if we go back, that's what this study is looking at, and it's very tied to the electronics and hydrophobic nature. Here, this is for side chains. Topless had proposed another tree, and this is to minimize what they call steric effects, which is basically being too crowded in the active site. So hopefully this slide makes a little more sense. So we were looking at extending this chain and looking at one particular branch of the topless tree here. And so this is something we'll revisit this summer. Now, in experiment 9, you aim to do a topless study of your own, but we were interested in compounds like this. We thought that this would have even better binding to MUP1 due to its basicity. But when we did our ITC study, you could see the spikes are going up. It's not giving off heat, heat is being absorbed, and it's not very much heat, but we're seeing this, what we say, weakly endothermic signal, okay, taking up heat, not giving it off. And there was no pKa in the literature for a compound like this. But what we suspect is that this is so basic, it would make a great hydrogen bond. However, instead it's just basic in water and starts deprotonating the water. And remember, when nitrogens already have a proton on them, they can't hydrogen bond, they can't act as nucleophiles. So we ran into a big problem with this. But imidazoles are less basic, and this just is adding, so this is a dihydroimidazole, 2 extra hydrogens on an imidazole ring, okay? So extra hydrogens when you take away the double bond. So this imidazole here actually showed some binding. We're seeing the curve get a little bit more similar to what we're used to. However, the binding wasn't great, and this almost looks like a little bit of a scatter plot, and this is just due to, we think, solubility issues. But this is in the old buffer, and we're really excited to have you explore our new buffer at the end of this experiment. So what you'll be doing in your first week is a synthesis we've laid out for you. And Rachel and Paul will talk to you a little bit more and lead a discussion with all the mentors about what's going on here, okay? For literature 6, you need to find conditions for this reaction. Now, this reaction is a reference that you should have found to do your pre-lab that was referenced in the background information I gave you. And literature 6 is its own thing, and you will submit to me a journal article that you find using it. Now, in the end, we are going to test these compounds in a certain way. We're going to test them by a new form of spectroscopy, which allows us to prepare them for ITC. So week 1 is here. Week 2, we're going to do this reaction to turn the dihydroimidazole to the imidazole. And in week 3, we're going to analyze this compound a bit more to prepare it for ITC. And I've had R groups on here, and so you should know, based on the aldehyde that you are using to do this reaction, this is the aldehyde, looks almost like a carboxylic acid, but an H instead of the OH. So your aldehyde was assigned to you. But when we're varying R groups, we can think about a lot of stuff. So here's your top list study, and you can see this on your poster for the URF, but I just wanted to show you what our groups can look like, okay? They can just be simple alkyl chains or rings that are made up of hydrocarbons, and hydrocarbons are just like they sound, hydrogen and carbon. Alkyl is just a hydrocarbon chain. You could have alkenes on there and triple bonds, which are alkynes. You could have these polar electron, we say, releasing groups, or you could have groups that pull electrons toward them, and these all should have different effects on binding. So I just wanted to give you an example slide that showed you, what you can dream up maybe next semester if you're going to be continuing on with the stream and developing ligands of your own. Thanks for your attention, and I'm again very sorry I couldn't be there today.